Hello and welcome back to the Oxford Online Maths Club. My name's James and I'm joined today by Jonathan.
Hello, I'm Jonathan. I'm a first year undergraduate studying computers and mathematics at Oxford.
Hey.
And today I'll be telling you about something that feels a lot like magic when you first see it, but even as you study it more, it still feels like magic. So it's actually really fun, and I'm going to take you through it.
Hey.
So to start off with this, you can see that this is Satoru, a Japanese cartoon figure. If you know him, then it'll be fun. But you can approximate him with this drawing, and if you see closely, then we can actually draw him as something on a grid. And you might wonder, what's the area of this figure? And so actually we can do something more interesting. Let's say I have this figure. So it's a very rough Darth Vader head from Star Wars, I suppose. But I'm a mathematician. I like weird shapes. So let's say I want a swimming pool for my future house to be in this shape. And I want to know how much tiling I need for it. So need to know how much tiling I would need. How on earth would I figure that out?
Can we ask
Well,
chat? Can we pause for a second and ask chat? Sorry, chat's here too. Hello, Lala in chat. Hello to Ruben, who says hi to both of us.
oh,
I sort of think they learn some strategies, and I kind of sorry to interrupt you, but I kind of want to know what they already have in mind for how to find. So you want the area like inside. It's actually not obvious when I look at it the first time which bit's the inside. I think you're pointing at it now, right?
yeah,
That's
yeah.
the inside.
It's the closed bit. I hopefully I'm not having like the rest of my world be the swimming pool and
That
that's the
does
only.
feel greedy.
Okay.
The swimming pool of the
But
ocean.
first, before we try and dive into it, let's look at a simpler figure. So, what do you guys think is the best way to find the area of this one?
Okay, I think that's more approachable. Yeah, yeah, yeah. Okay, okay. So we're gonna find the area of this shape. I think we're live. I think I've pressed all of the right buttons. Should have said. And I think I've got the audio set up right. Yeah, because I think at school, thinking about the areas, I think I learnt about area of a rectangle, area of a triangle, and then I think in A level, trapeziums were very important for some
Right.
reason in A level. Um, but then, yeah, so hi to Rex and Murray in chat. And Ruben says split it up into multiple triangles.
And yeah, exactly. So that's probably the first and most natural idea we'll get to. So we're going to split up into triangles. Maybe we do this. This is probably the most natural splitting. And so to
Ooh,
calculate the area, what we would probably do is say, well, this side, this has side length 2, side length 1, and so the area of this triangle here would be 2 times 1 over 2. This has area 1.
yeah.
And then for this one, similarly, we have 2 and 2. So this one has area 2. This is 3 and 2, so 3 times 2 is 6 divided by 2. This has area 3. And finally, this small triangle has area 1/2. So the total area here is 1 plus 2 plus 3 plus a half is 6.5.
Someone in
So,
chat's got two triangles and one trapezium. So I'm kind of interested how
well,
they're
that's
splitting
interesting
it.
also. I'm sure there are lots and lots of ways. I
Yeah, where's the
couldn't list
trapezium?
them all. You give me 100 years, maybe I still wouldn't get them all. But or maybe 100 years is a
I'm
long
kind of
time.
surprised you put one of. I'm not. You said it was natural, and I have to take you off on this because one of your points that you've got there, triangle two, or sorry, the triangle with area two.
Yeah.
One of the corners is halfway down the edge, and one of the corners is just floating in the middle, which of course
Right.
is fine. You know the area of those right angle triangles.
Well,
But
if you want to think about it, for if you want to make it solely triangles, then this one, I guess you might try to do this, but that's not good.
oh, maybe I'm
But
stupid. I was going to join it. You know, like when you're trying to prove to someone that the interior angles sum up to well, it's a pentagon, so 540. Maybe this is stupid. I would draw lines between vertices or like
oh
corners,
right, right.
and that maybe is silly because I know I'm going to have to think really hard about how big these triangles are.
Well, you could do that, but it's a little that's also
Oh yeah,
valid.
yeah,
But I
okay.
think the idea behind decomposing it and why it's so natural is that we decompose it into right angle triangles,
Right.
which importantly line up with the coordinate vertices. So that makes the area
Ooh.
calculation a lot easier.
Patrick and Ruben have both said you can draw a square or a rectangle around the whole shape and take away exterior
That's exactly
triangles.
right. So the next idea we might have is to do this. So we draw a
I like
square
that.
around it, which has area, like this side is 4, this side is 4. So the area of the whole thing is 16. We actually, we can switch colors for the inside. So the area is 16. minus, and then let's calculate the area of the ones inside. So this triangle here, this one has
Three
side
plus
length 3 and 3, so this has area 4.5.
Yep.
This side is 1 and 2, so this has area 1. This is 2 and 3, so it has area 3. And finally, this is a square. If we really want to be strict about triangles, we could do 1/2 and 1/2, but it's just the square of side length 1. It has area 1. And so we find here 16 minus, and then I'm just going to add these together. It's 9.5.
Nice.
Which works out to be, unsurprisingly, 6.5. So you see, there are a lot of ways to work out the area, but they all required a lot of calculation. Oh, and I don't know if anyone said this yet, but there's also, if you're a big fan of doing a lot of work, okay, so yeah, there's this triangle one that we could do like this. Or we could use the shoelace theorem. If you assign coordinates to all of these and then work out a certain formula for these, then you can get 6.5, but that's a lot of work. We don't really want to do that. And
I think I
also,
didn't learn the shoelace formula just quickly because people will ask. I think I didn't learn this at school. Maybe some people in chat have learned this at school. It's not where we're going with this, so I don't want to slow you down too much. But there exists some sort of slightly mad formula where you draw in like a shoelace pattern, and then you multiply pairs of numbers together, which is why all of those put points in there are multiplication. I think in your formula.
yeah,
You're like
yeah,
1 times 5, 2 times 2, 5 times 2. Like, goodness, you just
yeah,
combine to get all the coordinates. I don't know if
yeah.
you've seen that.
It's um yeah, it's not my topic. Well, it's kind of the point of my topic today is that there's a way to do it significantly easier than this formula that is kind of nasty. All right. So moving on from that, we can do better than both we can do better than the bounding box, and we can do better than the triangular decomposition, because all of those involved adding and multiplying and dividing a lot of numbers. But actually, let's do something more interesting. So I'm going to highlight all the inside points in blue. And so we can just note how many blue ones there are. There are 4 of them. And so actually we'll call these I for interior points. And then we can say, well, how many boundary points are there? There are 1, 2, 3, 4, 5, 6, and 7. So we'll call that B. Now I want you to look at what I plus B over 2 minus 1 is. Well, we know I is 4 plus 7 over 2 minus 1 equals, well, surprisingly or
Surprisingly, yeah.
unsurprisingly, given what I've been leading up to, it's 6.5. And it might seem like a coincidence because I plus B over 2 minus 1 seems sort of arbitrary.
Yeah.
And so this is like magic, right? Okay, so I'm going to tell you, this is what's called Pics theorem. It's that if you count how many points are inside and how many points on the outside, then the area of the whole thing is the number of inside points plus half the number of outside or boundary points minus 1. And this is crazy, right? It's like, wow, that's so strange. I don't see any connection.
So
But
this is
actually,
for polygons where it's made of. Oh, sorry, you've got a theorem statement. Sorry, it's just for
well,
ones with straight lines, right? Between whole number
right,
points.
I guess I should say that. So this is
No, no.
valid for lattice polygons, which is basically a fancy word for shapes that have all of their vertices, which are like the corners, lying on points in the grid. And actually, this has more applications because if you take any polygon, then you can always make some grid that's close enough to it. So yeah, you could always extend that like that. Okay. And so there's no need to read through all of that. It's just what I've shown before. So if you have a polygon whose vertices lie solely on lattice points, which are just the integer coordinates, then the area of the polygon is 1 plus b over 2 minus 1. Okay. So for example, I drew this already, but if we see I is 4, b is 7, and then the area works out to be 6.5, like we found with all the other methods before. Okay. How in the world can we even prove this? Let's think about it. So when we're considering areas, what was the first way we tried to find the area of the polygon?
How did we start? Oh, so we started. Well, let's ask chat. So we started with triangles, right? Or by
Yeah, exactly.
lots of right angle triangles that were drawn, and you said that as a kind of natural way of drawing on right angle triangles.
Exactly.
But
So the key thing here is triangles. Triangles are basically the simplest geometric shape aside from maybe lines or points, but triangles are really nice and they're easy to work with. So maybe we should start there. We can break every polygon down into triangles. So for example, this one, well, we've already done this, but instead of doing the one that I did before, I'm going to draw a slightly wonky decomposition, and then I'll tell you why in a little bit. So what we're gonna do here is we're gonna do this. So this is going to look almost the same as before, but there's going to be something a bit different about it this time.
ooh, this is not the method that anyone in chat wanted to use for the area of that.
No,
Oh my
this might
goodness!
seem a little
You're still
strange.
adding triangles.
Okay, this should be
What
right.
was that?
So now these are all triangles,
Agree.
but there's actually something nice about them. These are all small triangles, right? You can see that I've broken these down into all small triangles, tiny triangles that either look like this or maybe something like that. They're all kind of tiny because notice that before what we did was maybe we had some bigger triangles, like we had, I think this entire one is a triangle. No, no.
Yeah, it was huge.
Yeah, we had some large triangles, and maybe that's not a good idea. We should always start simple, perhaps. So we break it down into the simplest possible triangles. Now, these triangles, they have a name. They are called primitive lattice. They are called primitive lattice triangles, and that might seem like a big word, but actually, what a primitive lattice triangle is, basically, it's a triangle with no points on the inside and no points on its boundary except its corners. So I've already drawn a lot on the last slide, but some examples of them would be, I guess, use lines, would be this one, because notice that there are no points on the inside, like that one's over here, it's not in there. And the only points on its boundary are its corners. And so another example might be this one, or yeah, you can draw one at home. There are a lot of different kinds of primitive lattice triangles.
An anonymous person in chat points out that those two have got the same area because of like base times height. They've got the
Oh
same.
yeah.
If you call the top bit the base, then they've got the same height as each other. In fact, I think you could pick any point in the second row, and they'd have the same height.
Exactly. And so that's pretty interesting, right? We want to calculate the area and we can break it down into these triangles. And if we draw a lot of them, we can see that it looks like they kind of have the same area. But one way that we one way that we might want to try and prove this is that, well, base times height, right? One interesting thing is that if we look at what these triangles might have in common, it's that, well, they have at least one side parallel to a coordinate axis. And we can always use that as the base. And we say, well, it has side length 1 and it has like a height 1 or something. And so the area is 1 times 1 over 2, which is 1/2, right? But actually, there might be something more complicated than that. How do we show that each primitive lattice triangle only has at least one side that's parallel to a coordinate axis that's like from one point to another directly adjacent to it? Do you think that all primitive lattice triangles will look like this?
So slowing it down. Sorry, you've told me a primitive lattice triangle is one where there aren't any points on the inside,
Yes.
and there aren't any lattice points, the black dots. There aren't any lattice points along the sides. The only place where the triangle meets any black points at all are the three corners. And question, and it feels like a hard question, is all such triangles have one side that's length 1 and parallel to the grid.
Yeah.
That's hard.
This is my prompt.
I'm kind of imagining a triangle that picks out three random points and just sort of manages, I guess it would be quite skinny, but manages to be like at a weird angle and just miss all of these. But
Right. So it seems like that might be possible, right? But then it might not
really
be
long and skinny, but somehow just like dodging all of the lattice points on the way across. Maybe not.
Yeah. So when you're watching this, you can maybe try drawing. If you have a piece of paper and a pen nearby, try sketching out some dots of your own and then drawing out some, because you might try like, okay.
So far this year, every live stream for Maths Club has got me to draw something. So people who've been watching along have seen me try to do origami live. We tried to do some magic square stuff. What did I draw in magic squares? I can't remember. But there was something defection last week. Everyone's trying to get me to draw this. I'm sort of worried about this very wise triangle.
Yeah.
I suppose I shouldn't
Hard, right?
use the result because we're trying to prove Pics theorem.
No, of course not.
I'm trying
Yeah.
to prove Pics theorem, but if I believe Pics theorem in my heart, then these triangles have got 3 points on the outside, no points in the inside. So if Pics theorem is true, then these are all going to have area 3/2 minus 1/2.
Yeah.
Okay.
Which is, I guess, what some person said, right? We can look, well, for example, this one is the simplest primitive
That's
lattice
got area
triangle.
1/2, or moving that point along.
One. So this is 1/2.
Lined up.
Maybe while you like think about it, I'll draw some more.
Chat, I need you to help. So we've got like 6 corners, but you're not allowed any points inside the triangle, and you're not allowed any sort of weird points halfway along the boundary. Maybe if no sides are parallel to the grid, says chat, but I think I've been challenged to prove that doesn't happen. That there's never.
Or that it does, if you can find a counterexample.
Oh my goodness. Okay. So I'm imagining a triangle where I've got a cursor as well. This is the weird thing about this. I can point too. I'm imagining a triangle like from here down to here for a kind of start. Or you can't see this. Sorry. Bottom of the red triangle, down 2 and across 1, to the left.
Oh.
Yeah.
Like,
no, down 2, down 2 on the lattice.
okay.
I don't know what I'm trying to do. I'm trying to build a counterexample, but I suspect there aren't any. So yeah, down a bit more. Yeah, that line. That feels like a good start because I've dodged all the lattice points.
Okay.
So then, right, okay, so, what is going on here? For the 3 corners, I'm interested in whether you have
start there. Let's redraw it over here.
Okay. So I've tried to make those have different values for their x coordinates and the y coordinates, but now I think I am stuck. I don't really know where to put the next corner. Not over there on the left because there'll be something inside.
Rolling stuff out, right? So it definitely cannot be here. Cannot be there because that would make it parallel. Cannot be there because that wouldn't be lattice. Sorry, it wouldn't be primitive. Can't put it there. Can't. Well, we could put it there, but it wouldn't. It would have a parallel side. And then none of these are right because then they wouldn't be primitive lattice. And this one, well, that would have this side, so it can't be this one either. And this one would have a parallel one, so it's not this one.
But what about this one down here, down and left?
So this one, right? What happens if we do that? Then we just.
Oh wait, it wasn't true.
Oh, look, we found a counterexample already.
Hooray!
So indeed, this is not true. So the proof is not that easy.
So that's what. Okay. Sorry, that's a reminder to me that I should, before trying to prove something, I should try and check whether it's true. I feel like I've misled chat now. Sorry, chat. I tried to bring you along my side to prove something that wasn't true. Oops.
It's funny though. So yeah, a lot of results, like you might have a certain intuition that it might or might not be true, and then it turns out that either you think it's true, but then there's a counterexample, or you think it's false, and then it turns out that there is a proof because you just try as hard as you can, you can't find a counterexample.
Ruben in chat gets to say "I told you so" for spotting that there was one of those hiding in your lattice polygon from before. But
indeed there was actually
down the bottom left side, I think.
Right, that is true. It's true.
Right. Okay. So you're splitting up in general. You're splitting up a polygon into these primitive lattice triangles, and I've now realised that I know nothing about primitive lattice triangles.
That's all right.
They might. That still looks like it's got area 1/2, maybe.
Yeah. Okay. So just for fun, we might work out the area of this one. So we say, well, it feels like a cheat, but we're gonna use the bounding box method. So here, this entire rectangle, it has area, well, okay. It's 2, this is 3, so it's 2 times 3 over 2, which is 3. That's the area of the whole thing. I guess I should probably be drawing this one in red. And then we look, well, okay, let's actually split this up here. And now the triangle over here, it has side length 2 and 3. So, Sorry, no, okay, this one was not quite right. Sorry, the area of the what do you call it? Of the rectangle is 2 times 3, not 2 times 3 over 2.
Mm-hmm.
Uh, 2 times 3 is 6. And then the area of this triangle would be 2 times 3 over 2, which is 3. And then you can work out for yourself this area here, it's 1 and 2. So that would be area 1. I guess we can just draw these. And
There's 1 for
so,
the square and half for the little triangle underneath. So
indeed.
I think it does turn out to be 1/2 for that weird,
Indeed,
skinny,
it is.
primitive lattice triangle down the middle. It's also got area half.
Right.
Like all the
So we
others.
might suspect that all of these have area of a half. And it turns out that this is not, unfortunately, not the easiest thing to prove. So we're not going to do this. But we can
Okay.
just, yeah, it's almost like we have very good reason to believe that it has area and a half. You might be tempted to just use Pics theorem and you're like, oh, well, there are no points inside and there are no points on the outside aside from the boundary points, which is 3. So it's 3 halves minus 1, it's 1/2. Not well, this is gonna be essential to our Pics theorem proof. So we can't do that, unfortunately. Okay. Now that we have the area of a primitive last triangle, we're just gonna say it's 1/2 from now on.
Okay, so you're splitting this thing into small triangles that all have the same area, and now finding the area overall. If you believe that these primitive triangles all have area 1/2, you just got to count them, right?
Right. Okay.
Yeah.
So we're gonna say we take any lattice polygon. So yeah, any polygon that we has corners part of the grid. And then let's pretend that has I points on the inside and B points on the boundary, because that's what we're trying to show that can be expressed in terms of only these two quantities. Let's say that we can break it down into TPLTs, which just stands for primitive lattice triangles.
Mm.
So if we go back to, I think that's, okay, no, that's not there. If we go back to this one, then we will have how many primitive lattice triangles? Well, I'm just gonna
I
real
can't
quick
remember.
draw this back
I
again.
think it was
Oh,
13.
13, okay. That I think that's the right number, so I'm just going to go with that. We have 13 of them. Okay. And can anyone see what the area of the polygon would be in terms of T?
Oh, so in general, so before there were 13, but in general, if you've got
Yeah.
T for how many of them there are, then hmm, I guess if you truly believe that all of them have area 1/2,
That's a
there is
given.
there is a slight awkwardness here that I didn't tell you about, which is that there's about a 20-second delay between between asking a question and it getting out the internet and then them typing and it coming back in again. But that I've now bought us enough time that Anonymous in chat has said T over 2
Oh, that's all. That's all right.
for the area. Yeah, okay, so T of them and they're each area 1/2. If we believe that, then T over
Indeed.
2 for total.
So the area is T over 2.
Okay,
So we've established that. This seems to be right. We're going to say that.
just got to
Okay.
count them now.
Right. Oh, and then if you go back to the other example, we had 13 primitive lattice triangles, each with area 1/2. So it's 13 over 2,
Mm.
which is 6.5. And then, I mean, I guess that's also a valid way of calculating area, breaking it down into primitive lattice triangles. And that's not a lot. That's only like drawing and counting, but it's a lot of drawing. I don't think you want to do that.
Okay.
Okay. And so what are we going to do? Well, this is going to be cool because we're going to bring in a bit of graph theory but we're not going to treat it like that because it requires a bit more framework and the notion of a graph and a planar graph. So what we're just going to say is there's this result called Euler's theorem that I've restated a bit here. Basically, it says that for any dissection, okay, so I'm using the word dissection, basically it means any splitting that we take, like for example, we draw something like, I don't know, that. And then let's pretend that this is a primitive last triangle splitting. This is probably for a reason someone can tell me, or if you think there's probably some reason that this is not possible to be a primitive last triangle decomposition, but if you pretend that it is, for any dissection, then if you have T regions, which is just T triangles because we're splitting them all into primitive last triangles, and V vertices, which just means all the points. But actually, okay, I probably should have drawn something like this. The nuance here is that when you say V vertices, it doesn't mean only the boundary points. It also includes the inside points. and E edges, that just means the all of these lines. So that includes all the lines on the inside too. And so what we're going to do is take this as a given also, but it's an interesting proof. Well, okay, it's
Can we
not
pause
that
to
much.
talk? Can we pause and talk about Euler before it gets used and moves us on? But because I think somebody in chat called Euler's theorem. No, not somebody called Euler's theorem. Somebody mentioned Euler's theorem. You could set your username as Euler's theorem if you really wanted to. Slido chat is anonymous. You can put it to be whichever theorem you like. They called this earlier because they saw the idea that it was kind of invariant and doesn't depend on the kind of shape of the thing. There's a link here. If people have seen Euler's theorem before for, I don't know, for platonic solids or something. Have I got any platonic solids? I do have a platonic solid. I can go. If you've seen Euler's theorem before for some sort of platonic solid or something, where you've been told there's a relationship between the number of vertices, the number of edges, and the number of faces, then for a polyhedron or something, you might have seen a version that says vertices minus the edges plus the faces is 2. Jonathan's formula's got 1 on the right hand side, but there is a connection, right?
Yes. Okay. So well, if it's 1 instead of 2 because in the actual formula you would instead of T regions it would actually be F for faces and faces. So let's say we have some graph that looks, I guess, let's say it looks like that, and then we divide it somehow, like maybe like that. Okay, that's not very good. Let's do it a bit better. If it looks like that, then there aren't 4 faces. Actually, there are 5. It would be this one, this one, this one, this one. But where's the 5th face, you say? It's the outside face. So we count the outside as its own face.
If you
That's
like,
not really.
it's like the rest of the surface of the Earth. You've drawn that on a bit of the surface of the Earth, but there's this other enormous face for the rest of the planet. And if you zoom out to a solar system scale, then you get a little model that includes that graph, but it has this extra face for the rest of the world. And then the theory from Euler characteristics on polyhedra applies because you've got something that looks like a sphere.
Yeah. So in general, it'll be that V minus E plus F is this quantity for some polyhedron would be called the Euler characteristic, if I'm not mistaken.
Yes.
Then
Rex in chat agrees Euler characteristic is the thing to say.
Right. So in our case, this thing called a planar graph, which just means like a bunch of dots and connections between them that can be drawn inside two-dimensional space without any of them cross each other, then we know that this is always going to be 2. And then for us, F, and that actually kind of makes sense if you think about it. It's like you take the entire world or just your sheet of paper if you're feeling less ambitious. Then if you only take this to be 4 faces, then what happens to the rest of it? No, you want to include all of it. So it's kind of like a partition of the entire piece of paper. So faces also kind of make sense.
There's a link. So someone says, where does that face end? And that's why I've been clear that I'm talking about doing geometry on the surface of a sphere. If you're doing geometry on a flat plane, then you just get a different number because doing a geometry on doing this kind of graph theory on a flat plane is just different from doing it on a globe. If you do it on the surface of a torus or a donut instead, then it's different again. So I've got a torus. There's a shape where you can count the vertices, count the edges, count the faces, and you don't get 2 or 1, you get 0, which this matter is linked to topology, this idea about what shape of surface you're working with. So the question in chat, sorry to pull it out, but the question in chat that says, where does the face end, is a good question, because if you don't think about where this is going or how it joins up around the back or whatever, then you can change the answer, you can change the number. But that 1 on the right hand side, if you like, it encodes the idea that we're doing this graph theory on a flat plane. Ish? No.
Well,
no, we're doing it on the and we're not counting the outside face.
Yeah, the outside face. Well, the lucky thing is that for our purposes, the outside face doesn't matter to us, so we're just going to take this form of a formula for it. Because yes.
Yeah. Sorry for taking you off on a mad tangent to talk about the enormous face that's the rest of the world, but that's not part of our polygon, so we're not going to count it.
No, feel free to interrupt me at any time. It's an interesting tangent. Okay. And so continuing with our journey on the way to proving Pics theorem, we just take Euler's theorem, which says that v minus e plus t is 1. And recall that earlier we showed that the area A equals t over 2, where t is the number of triangles, which is also the number of regions. So I picked t to be the same because these are the same t. They're the same t. Okay. And so if area is t over 2, then we'll probably want to find some expression in terms of t. So by this formula, we know that area is t over 2, which is the same thing. Okay, so we'll kind of want to find t, right? So let's write this as t equals e minus v plus 1. This just follows from that. And now the next thing we want to do is perhaps, okay, we have t equals e minus v plus 1. Now, we want to find like this number in terms of probably I and b eventually, the number of points on the inside and the boundary points. So what we're going to do is try and express e and v in terms of things that we already know. So I think the easiest one to start with is v. Going back to what I told you earlier, if we take, let's see, what's happening there? Okay. If we draw some polygon and then divide it somehow. Okay. And anyway, if we divide it, then the number of vertices is the number of points, including the ones on the inside. So that would be all of this one, this one, this one, this one, this one, this one. So in terms of like I, B, T, whatever, what is V? You should be drawing it up there.
The total number of vertices. I've got to remember your letters for these things before, I think. We talked about boundary points and we talked about interior points. And pause to think because, yeah, I plus B, says Anonymous in chat. Euler's, somebody set the username to Euler's character, well done. Inner points plus boundary points.
Indeed. So V is I plus B, because if you think about it, well, okay, I'm just gonna recolor some of these. If you make the inside ones blue, the outside ones red, it's evident that vertices are just, well, each vertex is either on the inside or on the border. So it's just number of inside plus number of border. So V is I plus B. That was good. That was nice. How about E though? That's a little more challenging. It's not immediately obvious, so we might want to think about it. How do we count how many of switch colors? Orange, how exciting. How do we count how many of these things there are? Like here, we'll see that actually probably yeah, okay, I have this one again. So let's just try it going back to our original example. I'm going to redissect this one and we'll see how that goes.
Counting edges. Okay, so you're going to split this in primitive triangles.
Yeah.
I've realised that the reason you need them to be primitive triangles, or one of the reasons anyway, is the primitive triangles are not allowed to have any points inside them. So there's not any missing points. I'm sorry, if you just said this and I missed it.
No, that's exactly right.
Yeah, this idea that you don't want these tiny triangles that you're drawing to have any points inside because you're trying to say we've got all of the vertices, B plus I, we've got all of the boundary ones and all of the interior ones. We don't have any like leftover ones that are floating inside one of these triangles. Ooh. No.
Okay.
Pause, it's chill. Oh, it's back, it's back. Okay.
Indeed, okay, well, this one is just the sneaky example that we did not see earlier.
There's a suggestion in chat that every two adjacent points have one line, but what does adjacent mean? How do you know?
Okay, that's kind of along the right tracks, right? So if we want to say like, well, colors,
because the primitive triangle at the bottom there has nothing to do with like tricky.
Right. So if we indeed had primitive last triangles, all of them had a side parallel to coordinate axis, then we might say, well, these two share an edge, and maybe these two share an edge. But it might not be immediately obvious how you might proceed from there. So then what you might say is, well, what do we know? Well, the most obvious things are that we know I, the number of points on the inside. Well, we know B, the number of points on the outside. And there might be a third quantity that we have not considered yet. So actually, we're going back to what we have. We have a equals t over 2, and t equals e minus v plus 1. And we already found v, but I'm not going to write that down. So we might seem like we're not allowed to use t anymore because that's what we're trying to find, but it's just a linear equation if we put it in terms of t. So we can still like solve for t even further if we have it in terms of t. So with this revelation that we can actually put it in terms of t, then any ideas?
Okay, so question, maybe that's not our final form of equation. We might need to do more manipulation algebraically. But you're asking, how many edges are there? And you're like, oh, it's not just the red lines, is it? Because you count the
Sorry,
ones going around the
I should
outside
probably
as
be highlighting these.
well.
Uh,
How many edges? If you've got T triangles, how many edges have you got? But that's, I think, not quite. I've misled them there a bit.
No, actually, it's like misleading, but that's exactly how we're going to calculate it. Okay.
We've got T triangles, and I know how many edges a triangle has got. The right answer is not a 3T because.
So let's write down E equals 3T because just as a start.
Triangles have got 3 sides.
Yeah, there are T triangles, each has 3 sides.
Yeah.
3T. What could go wrong? Okay, but the first thing that might go wrong is that we quite obviously let's look at this one. Well, we count it once for this triangle, but then we count it again for this triangle. So it seems that we've counted this one twice. And similarly, if we look at perhaps this edge, then it's been counted by this triangle, and it's been counted by this triangle.
Yeah.
So perhaps we divide by 2 to have each one only counted once. So this is pretty promising, 3t over 2. But actually, this is not quite right either. Does anyone see what might be wrong with 3t over 2?
I really want chat to join in to check that they followed the thing we said that was false, the second thing we said that was false, and they're going to save the day. Because the number of edges in the diagram is not 3t because some of the triangles put together, and it's not 3t over 2 because this is not just double counting. It's not always the case that 2 triangles meet an edge, but we're close. Which ones are? How do we fix that? It's almost always the case that edges are 2 edges meeting together. Ginger Biscuit's halfway there. Ginger Biscuit in chat says subtract the number of edges on the outside. They've spotted that it's the kind of crispy outside ones that I made you draw in, but how many of those are there?
Exactly. So there's something interesting going on with the outside ones.
Harry Ball Theorem says we need to double count the boundary edges before halving. So you want to like add the boundary ones.
Yeah, sure.
Okay, so what you do?
Right, so we've seen that there's something going on around the boundary points, right? So what happened when we did 3t over 2 was that, well, we said each of these are counted twice, so we divide by 2. But in reality, each, like, let's say this one, it only has one triangle to count it, and none on this side. And so this was only counted once. And when we divide it by 2, it's only counted half a time. So what can we do for that? Well, it's counted half a time. We want to count it once a time, I suppose. We can do the most obvious thing, which is just literally add. So however many there are, we'll fill that in a bit, over 2. Yeah.
Just getting that.
Yeah, number of boundaries.
Boundary edges, yes.
Yes.
And I think chat's managed to make the last leap, which is the number of boundary edges. Feels like an unknown, but actually we do know the number of boundary edges. It's equal to b, the number of boundary points.
Exactly. And so we can spot here that, well, for each of these, we can just map it maybe to the clockwise point or counterclockwise. It doesn't matter. We can just say for this boundary point, we map it with this line. For this boundary point, we take it to this line. We do this for all of them. And then we see that there's like for each one, there's another one. So we know that they're exactly b of these here.
And now I see why when you set up primitive linear
lattice.
Triangles?
Lattice triangle.
Primitive lattice triangles. When you set up the primitive lattice triangles, you said they're not allowed to have a point along the edge. We're using that now because we're looking at the edge and saying all of the points are just one and then an edge and then a point and then an edge, and no sort of sneaky extra boundary points halfway along a boundary edge. Yay. Okay, so we've got algebra now. Algebra to finish the job because you know E in terms of T and B, you know V in terms of I and B. You want T, you have an equation on the right hand side. It's all coming
Okay.
together.
So let's go through that. Okay, so I'm going to erase that. So we've established A equals T over 2. T equals E minus V plus 1. V equals I plus B. And now we've shown that E equals, what was this again? 3T over 2 plus B over 2. Not mistaken. So then what we have combining these all together is that T equals 3T over 2 plus B over 2.
E and minus.
Yes,
Yeah,
this
carry
is
on. Yeah, that bit's E.
wait, I can
I'm
actually
playing
be
along.
color coding these.
Oh.
That would be nicer. Let's see.
Yeah, we've got time.
I think I'm going a bit too fast. I'm gonna finish before time. That's all right though.
We got time. We got time. Don't worry. Olive in chat has. I guess Olive might have missed the start where we had this shape because Olive has just managed to follow this through. I think to find the area of the shape.
Right.
So
Right.
6.5 is coming up.
Okay.
Which is where we started, but
So
we're
now
now
we
playing
can
around with Pics theorem.
so no, T equals, and then in blue we have 3T over 2 plus B over 2 minus, and then in red, I plus B.
Yep.
And then just plus 1.
Yep.
And so we can do a bit of algebra, moving this to that side, or not the other way around, this to the side, distribute the negative, whatever. It's a bit of work. I mean, I have plenty of time, so I might go through it.
We
It's
want
not
T over 2, so let's not multiply up because the
right.
area is T over 2, right? Yeah.
Plus, and then it's B over 2 minus I minus B plus 1.
Yeah.
And then these two become minus B over 2, so we'll just move that to the other side. Move it all to the other side, basically.
Yeah, we want T over 2.
So we have T over 2.
Move everything over.
Yeah, except T over 2, I guess. That stays there.
Okay, yeah, that's
T over 2 equals I plus B over 2 minus 1. Wait a minute. And A was T over 2.
Yeah.
So we've just showed that A is the number of interior points plus half the number of boundary points minus 1. And that's exactly the statement of Pics theorem. Oh, we've proved it. Yay.
And along the way, I'm making notes for the further reading. So I love that. That's brilliant. Notes for further reading. I've got to tell people about Euler characteristic, which I didn't see coming. I didn't know there was going to be Euler characteristic in this. Chat saw it coming, but I didn't see that coming. That we'd have the v minus e plus t equals 1 fact, and also those primitive linear triangles. They're complicated. Primitive lattice triangles. Sorry.
So in general, a primitive triangle would be a triangle without points on the inside or outside, and then lattice just means they have other vertices on the these points.
Right. Okay. So primitive, it means exactly 3 lattice points. Yes. At the corners. Okay. Yeah. Okay. Got it.
Yeah. Okay. And we have plenty of time, so I might okay. So yeah, if you want to look at the algebra written out more cleanly than my messy handwriting, then it looks like a bit like this. So T becomes this thing, I plus B over 2 minus 1. Oh, no, sorry. T becomes this, so that means that T over 2 is I plus B over 2 minus 1, which is A.
Yep.
Ta-da! That is Fick's theorem. And so going back to and so for my swimming pool, if we count, it turns out there are 21 interior points and 52 boundary points. And okay, that might seem like a lot, but if we mirror it, because this is symmetrical, then we just count on this side, that side, whatever.
And so counting easier, I guess? Or okay, yeah.
Something like that. Then the area becomes 46, so I know that I have to buy 46 square tile, or it's not square tiles, but like square units of tiles to create my swimming pool's floor. Yay! And now going back to the initial hook, if we go back to the tutorial from a long time ago,
I was hoping this would come back because it's got holes in, right?
It wasn't clickbait, and we have holes in it. And then how are we going to account for those? Yes. These are called non-simple polygons if they have holes inside them. Okay. Well, this does seem like a Pics theorem thing. So we're assuming that in addition to the entire thing being a lattice polygon, then the holes are also lattice polygons. Then Pics theorem works really well for areas of lattice polygons. Well, of course, this is amazing. It's Pics theorem exactly. Okay, what can we do? I
Ah,
guess if we like assign names to these, polygon is P, so that would be the entire shape, the outline. Sorry, no, P is the shape including the holes.
mhm.
P0, P naught is the one is the entire outlines that would like fill in the holes, and then we have n polygons, which each one represents a hole inside P naught. So we were gonna number the call these H1 through Hn, each for holes. Oh, actually, these don't really matter. It just if you'd like to go through the algebra, then I have them on the next slide, but it's not very nice, and we're not going to go through it. But
Chat
and
says chat's got the idea of finding the area of the holes and subtracting them anonymous and
yeah, exactly. So what do you do if you're faced with something and then something you don't want? Well, you remove the part you don't want from the part from the of the thing you want. So it's the same for holes. We take what we want. Okay, I'm not gonna go through that. We take what we want. Okay. Which in this case would be this outline. And then we take the areas of the insides, which would be the sum of this area.
Look at that smile. Let me take away the smile as well.
To make
Oh, it's
be
going
faithful.
a little bit Joker. Yeah, good. Oh no, I don't like it. I don't like it.
We should change color to the eye.
But yeah, you subtract all of these bits. I'm trying to work out in my head if the I can't do this in my head, but possibly does it simplify? Does it simplify? Because like those if those things on the inside are also lattice polygons,
Right.
then
So you might
you
have
are
that
counting the
intuition.
points and then subtracting them, which is sort of fine. But then there's something going on with boundaries that I haven't quite got, where
Exactly. So you
do I
have
have
this
like a
idea that
minus sign because
maybe
it's
something more interesting is going on than just adding and subtracting points because you're adding and subtracting like interior points, boundary points that you already have. So you
ah
could work out like formally all the sums and the subtractions, but I've gone and done that for you, and I can actually tell you that it does simplify and it simplifies very, very nicely.
okay.
Okay, so let's look at this. Okay, the coloring does look too much like a clown for my taste, so I'm going to erase this real quick. Okay, so if we redefine the number of interior points to be the points like here, but not here, not in any of these, which makes sense because these are the points that are actually inside that are actually inside the shape. Oh no, it looks like he has chicken pox. Uh-oh.
Oh. Don't you try
But
it?
and then the boundary points to include to be not in addition to these to also include the boundary points like along the border of the inside.
So when I
With
do
this
the
new
outside
definition,
shape, when I do the outside shape, those interior edges, I'm counting them as actual interior. So Pics theorem says count them, and then when I subtract the interior shape, I'm subtracting the like b/2 stuff. They were on the boundary, so I subtract half. Okay, so my
that's
prediction is that they end up counting for half, right? Because they count once
yeah,
for outside shape, and then you subtract
yeah,
a
that's right.
calculation for the interior shape that has a half in it. And I don't really know what happens at the corners, but
Totally. You're on to the right idea.
oh,
So
I've got some
what
ones in
happens
there as well.
is that, well, intuitively, the interior points that are like within the gray region, they'll be counted once. These ones will be counted once, but then subtracted out by the area of this one by Fick's theorem. The ones on the borders, we want, okay, so the on the outline of the shape, they'll be counted b/2 times. Well, they'll be counted each half a time, which is what we want. And the inside ones, at first they'll be counted once because they acted like interior points. But when we subtract out the area of this shape, Pick's theorem tells us that half of the number of these is counted as part of the area. So when we subtract those out, then it's 1 minus 1/2. Each of these interior points counts 1/2 also. Sorry, not interior points. Each of these like inner boundary points counts 1/2 a time also. So this is kind of exactly, this sounds a lot like Pick's theorem, right? So now all these gray interior points count once, and all the boundary points, including the interior boundary points and the exterior boundary points, they all count half a time. And so, right, we didn't make any mistakes. This is exactly what it works out to. It's an ugly formula, but we have area of polygon is equal to the number of interior points plus half the boundary points minus one. But there's an interesting exception. There's actually a plus n, where n is the number of holes.
Right, so the thing, you end up with the same sort of punchline for Pics theorem, that you just count the interior points, like genuinely interior, not counting, not in a hole, and you count the boundary ones, including the like boundary of any hole. And then
Yeah.
you just do that like normal. You subtract one like normal, but then you add n for literally somebody said it's genus 6 because it's got 6 holes in it. You just add 6 to what you would do
Yeah,
normally. That's
exactly.
brilliant.
It's kind of funny because we have the minus one in Pics theorem. All right.
Is
And
that just a
so
topology thing? Is it just like if you know it's got genus 6, then can you write down Euler's theorem from Euler characteristic from before and just say
that's
n
true.
minus
I
1, right?
didn't consider
Is it
that.
just
If
is
we
it
can
just
also
a
write, yeah,
1 minus n instead of a 1?
that's
Possibly.
true. That's actually a good idea.
I think it's just changed the
That
constant
sounds
that you
like it
have
works.
because all the other lines work, don't they? That you're counting when you had that rule about b plus I, that's fine, and you had that rule which we worked out together, like 3/2, but not quite 3/2t.
Yeah,
I think that's invariant of like topology. I think it's just changing the constant. I think it's just Euler.
it should work.
I
Yeah.
think it's just Euler.
Wow. Indeed. And so
Oh,
if we
genus
want to work
6.
out,
Sorry, I said it and I shouldn't have said it. Thank you, chat, for calling me out. 6. When I say genus 6, I just mean that there are 6 holes. 2 for the eyes, 1 for the nose, 1 for the mouth. So 6. 1, 2, 3, 4, 5, 6, 7. 7.
yeah,
Genus 7. 2 for the eyes, 2 for the ears, 1 for the nose, 1 for the mouth, and 1 for the tummy.
indeed.
Genus being high. There's people who study donuts like this. I'll talk about genus.
And if you imagine,
Ginger Biscuit has got the thing in chat which has a factor of 2 in it that I don't want to think about right now. But
oh, what is this? Okay. Anyway,
think about
so
that right now.
using this revised formula, we can calculate the area. Perhaps I want like a cutout of Totoro that I want to make for like paper mache or something like that. There are so many reasons. You might want to find the area, and then Fick's theorem can help you a lot with that. So here we find there are 147 interior points and 116 boundary points. 147 plus this would work out to like 58. You add them, you get yeah, that's 205, I believe. And then 205, you add the number of holes, which is 7. So that gives you 212 and subtract 1, 211. That's the area of the figure. Ta-da! And so now we've tackled both the Darth Vader swimming pool and this cute cutout.
Nice. And there's a bit we've definitely. I didn't see it coming, but we've definitely got topology. People will think that's scripted because I have this Taurus ready to go, but that's just what my office is like.
Okay, we're not gonna get into that.
I
But
think we're gonna do it. I think that's a good place. We found the area. It's got a key thing about holes in.
there are a lot of other things you can do with Pick's theorem, and there are so many applications. And I think I want to circle back to the fact that even though we've gone through so much to painstakingly show that this is true, but it still feels kind of unnatural. It's like, okay, I'm faced with like this thing, and then you're telling me if I count how many things are on the inside and how many things are on the border, and then I like add three numbers together, one of which is -1, then I'll just get the area of the whole thing. Like I've been taught like, okay, area, I have to subtract this, multiply this, add this, whatever. But this is so simple. So I think that's really the beauty of it. Yeah, it's both simple, a bit shocking, surprising, but really elegant and neat. So that's one of the beauty of maths.
Yeah, that is good. I think for me, my takeaway as well. Well, would you get takeaway from chat as well? Oh, chat has noticed that I said two small numbers that were close together. Chat would like to know, can we do it for 3D? I should have maybe warned you that chat is always obsessed with complex numbers, which they haven't mentioned yet. But this is in 2D, so why not? Complex numbers and higher dimensions. Chat loves higher dimensions in particular. They'd like to know, is there a version of Pics theorem in 3D? I don't know what that would mean.
That is a really good point. Okay. So, if you try and reason about it, the simplest shape you can imagine in 3D is probably like some wedge, which is like a slice. Maybe like part of a rectangular prism. I don't know how I would draw that, but if you just imagine for yourself, basically if you work out the number of interior points and the number of boundary points, then you can show that it does not hold given only the number of interior and boundary points. So you can have two polyhedra with the same number of interior and boundary points, but they have different area. So unfortunately, it doesn't generalize that easily into 3 dimensions. There are ways you can do it, but none of them are like nearly as nice as I plus b over 2 minus 1.
That's a shame because I guess it must be hiding in that primitive lattice triangle fact or something that you
Yeah.
can't do that sort of thing in 3D. Ooh, intuitively they say it turns out that A is anonymous in chat says intuitively A is directly proportional to I. I guess like those points are in the interior, they're kind of surrounded by area. Proportional to B on like a 2-to-1 ratio because those points are like I guess they're like 50-50. Are they in the
Right. If you
shape or
want to go
not?
back
50-50.
and take a
And
look
then
at
there's
this,
-1, which is just a constant, they say.
we can just say like, okay, I just draw a square around me, which is area 1. But I'm a boundary point, so I get like half an area because only half of me is on the inside. So each of these like get a half.
And
I'm
I
not
can
sure how you would
see,
like deal
yeah.
with this one. The
And also
intuition, like
that line
it
down there
seemed
with
wet.
gradient -2/3 for the gradient of that left line.
Yeah, something like
It's
that.
pretty
It's
weird,
not,
isn't it?
yeah.
Because it's quite a long line, which happens to not go through any points. Yeah,
Yeah.
this is my first guess. To be honest, when you said the answer, Pics theorem is I plus b over 2, mumble mumble, I thought, aha, I can see a factor of 2 because they're like half in, half out.
Yeah.
There's an
But
integral
if you
theorem
look at
there.
like this corner, that's not exactly right. So,
Yeah.
oh, actually, this does. Wait, but this is actually really related to the fact that you told me earlier that the interior angles sum to, well, that thing, because the idea is that the average is 180. Like in essence, the average is about 180 for each one. Each one contributes a factor, an angle of about 180. And so that means it's about half. Each angle will be kind of like half, basically. So, well, that's not exactly right, but it kind of gives you a feel that half of it will be in, half of it will be out.
Yeah, maybe. Maybe. I'm still worried. I've just thought for a really large polygon, uh, I will be enormous because there'll be lots of interior points.
Yeah.
But B won't be that large because it's just like the perimeter. And
Yes.
area is like squares. If you have a shape that's like 100 wide and it's kind of roundish, there's like
Yeah.
100 squared points inside. So for a very large shape, the formula is just about count the points inside.
Yeah.
Which I guess means when I was very small, they told me you can approximate area by counting the grid squares that are inside. And then I think they might have said if some of them are like on the boundary, they count 50-50.
Oh, someone, yeah,
Maybe? And you've
participating.
shown me a way to make that more precise.
Yeah.
Instead of counting squares, count the points. And then you really can subtract boundary ones, or sorry, boundary ones count for half, and then just -1 at the end. I think that's nice. You take a kind of like an approximation or kind of like a thing that maybe your intuition that the interior points are genuine and the boundary points count for half. Made it really precise. I like that a lot. Cool. Right. We are coming up to 6 o'clock. If Jack's got any questions, there's a question about how to apply this.
How to apply this.
Yeah.
Okay.
Well, how is this applied outside of abstract geometry? Ooh.
Well, the swimming pool.
Oh right. Okay. Yeah. You genuinely want that swimming pool in the future, right?
Yeah,
Oh,
yeah,
that's
definitely.
practical geometry.
Hmm. I suppose any polygon, I think I mentioned this, but if you make the grid like arbitrarily small, then you can approximate any polygon with the grid and then use Pics theorem on it to get a good approximation.
Does that mean you can draw a polygon that's on a lattice really large and kind of like a circle, and then approximate pi? It's probably not a good way of doing it, but the
Yeah.
area is something to do with pi, isn't it? And like
Eh,
someone in chat
I'm
wants to do modern architecture.
That works too. I think the Pics theorem is one of those like really applied things. Like area finding, that's pretty general. I think that's already very strong in itself.
This is already on the applied end of
Yeah.
right. This is abstract because it's a formula, but there's a lot more math that's more abstract than this.
Yeah.
Yeah, I guess. Yeah, the fact that you're kind of tantalising close to finding a kind of like real world area um, opens you up, I suppose, to the question of what areas do you want to find. But when we had magic squares a couple of weeks ago, I don't think anybody asked what are the applications of these magic squares. Maybe they were thinking it. I don't know. Um, I forgot to do the how was your day poll, so I'm going to controversially do the how was your day poll at the end, because I would like to know how that day was.
How was your day affected by
How was your day affected by Pics theorem? Well, good for it. If everyone says they're having a great day, then I think that tells me about it tells me about viewer retention for one thing. Right? Yeah. people still here are having a great day, mostly, not entirely. Anyway, good. I'm happy. I think. How has your day been? Other than thank you for doing Pics theorem. Well, I don't know, chat while they're voting. They're having an okay day. It's going pretty well.
I've had a good. Yeah.
Oh, I've clicked on the wrong. I've now messed everything up, but that's just me, isn't it? Good. Okay. I think I've broken everything. Before I break anything else, I think I'm going to wrap things up. Jonathan, thank you very much for coming on Oxford Online Maths Club. We're going to be back. I've said two things. I'm going to post further reading notes tomorrow. There are several things we've mentioned that I want to link people to, like Euler's theorem and characteristics and topology and other stuff. Is there anything else? Is there anything that you would like them to look up if they enjoy this and they want to see something related? What should they do next?
That's a really good question. So, Fick's theorem is kind of like kind of feels like a standalone result, but I think the most relevant ones have already been mentioned. I guess Euler's formula for polyhedrons. We also found like an interesting link to topology in the holes thing, so you might want to check out like some readings on topology if you'd like that. If you want to explore further like how we might be able to generalize it to 3D and stuff. It is possible, it's just not as neat. So you could look into that if you'd like that.
Nice. Someone in chat says topology in all capital letters. Just topology.
I like this gear.
Nice. Right, okay, in that case, we will be back for another episode of the Oxford Online Maths Club in 167 hours. Until then, have a nice evening, have a nice weekend, but it's goodbye from both of us. Bye.
Bye.